Ready for the demo? Let's resume. So we will continue our discussion on second graph theory. Today, so far we saw the eigenspectrum of the adjacency matrix, the eigenspectrum of the Laplacian. We go into the eigenspectrum of the random walk matrix today. In the next few lectures, we'll do it, and eventually we'll come to the Cheever's inequalities. Before that, I want to talk about Cayley graphs and their eigenspectrum. So we're going to do Cayley graphs. What are Cayley graphs? These are graphs which are nicely defined, whose vertex set is an underlying some group, and the edges are according to some the group operation. So we're going to have in all of these, we're going to have some, we're going to work with some group G. So G, which comes with some operation. So this is a set of elements with an associated elements with an associated binary operation in the set. Basically, dot is a function from G cross G to G, and it has several properties. What is the first properties? It's associative. It has that is A dot B dot C is the same as A dot B dot C. It has what's called an identity. That is, there exists a E in G such that A dot E equals E dot A equals A for all E. Order, yeah. And this E is typically called the element 1. It's the unit of the 1. You can also show that if this unit exists, it has to be unique. And then I will need inverses. That is, for all A in G, there exists a B in G such that A dot B equals B dot A equals this. So that's the inverse element. These are all the properties I need. If furthermore you have commutativity also, then it's called an abelian. Furthermore, we have also commutativity. This is not required of the definition. That is, for all AB, we do have A dot B equals B dot A. Then G is abelian. And what are some examples of groups? Classic example, of course, is a set of all integers with dot being the plus operation. Another one, then you can go look at integers modulo. You can look at modulo some prime or any composite with addition. Here, usually when addition is the identity, addition is the operation, then if the operation is commutative, I'll usually refer to the operation by plus. If the operation is not necessarily commutative, we'll refer it with dot. That's one. Another one is what's F2 to the n, the Boolean hypercube. That is 0, 1 to the n, and the usual addition operation. Then non-commutative ones, for example, are GLN, GLN over, say, the rationals. That is, what I'm talking about is the set of invertible matrices with rational entries. And the operation is multiplication, matrix multiplication. You could look at triangular, upper triangular matrices, lower triangular matrices. There are various such groups that you could do. Now, we're going to define, most of you might have, some of you might have seen this. The reason I'm doing Cayley graphs is the eigenspectrum of a Cayley graph is very, very nice. And we'll see that for now. So what's a Cayley graph? A Cayley graph is going to be, the underlying vertices are going to be exactly the elements of the group. The group are going to be the vertices. And the edges are going to be defined by group operation. That is, you're going to move from one group element to another group element by doing a group operation. So the typical set of group operation we'll talk about, we'll have S is going to be some subset of G. And the Cayley group corresponding to G comma S is the graph whose vertex set is exactly G, and the edge set is, you take an element G and you move it by GS. So you take any group element and you move it by an element from the set of generators. So that's a Cayley graph. Notice by definition, the way I had defined it, the Cayley graph is a directed graph. That is, each generator lets you move in one direction. If S is closed under inverses, that is, S is equal to S inverse. That is, every inverse of S in the group is also in S. Then you notice the edge going from GS to G will be GS, comma, GS into S inverse. That's also a valid edge because S is this one. Then the graph is undirected. Then Cayley G, yes, is the undirected graph. This is a definition of and that's just because if you have GGS, then you also have GS S inverse, which is the same as GSG. Therefore, whenever you have the edge GGS, you also have the edge GSG if that's closed under inverses. And therefore, you can assume the underlying graph is undirected. If you have the property S is equal to S inverse, and almost all the constructions we'll see S will be equal to S inverse. So we'll only look at undirected Cayley graphs. Okay. Just to get this one, let's look at some examples. Example 1, let's look at in the case when the group is F2 to the N, and this set of generators I'm going to use are basically the identity vectors E1, E2, En, where Ei is 0, 0, except for 1 in the ith location and 0 else. That's the ith location. Notice that this is F2 is certainly, if every element it's its own inverse in F2. Therefore, this is certainly closed under inverses. So what is the graph that you get doing this? The elements are 0, 1 to the N. The vertices of the graph are 0, 1 to the N. What are the edges? What are the edges of this graph?
The binary string of length.
Huh? Yeah, that's the set of vertices. The set of vertices are all binary strings of length N. That's what F2 to the N. What are the edges of this graph? So our binary string, so let's look at the definition of Cayley graph. Our binary string is connected to another. So G, you operate it with S.
If they differ by one vertex, then
there's an edge. So what is this? This is a Boolean hypercube. This is exactly the Boolean hypercube. Perfect. So the Boolean hypercube is this has this nice scaly structure in which the vertices are exactly elements of f2 to the n, and two elements differ if the two elements are connected by an edge if they differ in exactly 1 bit, and that explains this whole thing. Look at another example. Let's look at G being all integers mod m. M is some positive integer. M is some, to be clean, that is, keep it as some positive integer starting from 2 onwards. And I'm looking at G to be set of all integers mod n. And the operation for me, the G is also, the operation is plus. The operation which I'm looking at is plus. Okay. And let's put S to be 1 and minus 1. Minus 1 is the same as m minus 1. M minus 1 is 1. Okay, that's my S. So what will the corresponding Cayley graph for this G and S look like? So notice its vertices are exactly those m numbers which are the residue classes corresponding to division by m. So it's 0, 1, 2, 3 up to m minus 1. And when do you connect two of them?
If they add up to m
Minus 1. No. So you take a particular, say 3. You look at m being 5. M being 5, let's take the vertex 2 in it. 2 is connected to which two vertices? 1 and 3. So notice, in fact, it's exactly the m cycle. So you put the m vertices and you're drawing the cycle. This is the m cycle. Cayley graphs are always regular because every vertex, what's the degree of every vertex?
2.
So this one 2. In general, what's the degree of every vertex? Size of S. Size of S. So Cayley graphs are in general regular. First, let's look at slightly more interesting examples. Called more interesting example in which the group I'm going to work with is set of all what are these? These are upper triangular matrices. Set of all upper triangular matrices where x, y, z are arbitrary integers.
The second time cycle, it will be self edges and the cycle.
No, I haven't put 0, no? It's only 1 and minus 1. So every vertex.
Okay, so everything else is as the group operation is addition, right?
The group operation is addition. It's not multiplication. It's not. It's the group operation is addition. It's one. Yeah. If S had the identity element, then there's a self loop. If S has an identity element, then there's a self loop. None of the S's that I have put here have the identity element. And by the way, this is an infinite. This one, and the operation which I'm looking at, the operation is matrix multiplication. It should not be hard to notice that the product of two such upper triangular matrices is also upper triangular matrix. It has an identity which is the diagonal, which is the identity matrix, the usual identity matrix. And you should also be able to check the inverse of any such guy will also be an upper triangular matrix with integer entries. That's important. It will have, and that's because the determinant of this is 1 matrix. So the inverse of this will also have only integer entries. And I'm going to look at S being actually, so I'm going to first define T to be these three elements. 1, 1, 1. This is all 0. 1, 0, 0. 1, 1, 1. This is all 0. 0, 1, 0. 1, 1. 0, 0, 1. There are three places, three non-zero, three places where the X, Y, Z, and putting one of each one of them. And S is going to be basically T union T inverse. I'm going to put its inverse also so that to make S to be closed under inverses. So this is a 6-element set. S. And the Cayley graph of this is an infinite graph on the set of upper triangular matrices, which is 6 regular. I don't have, this is called the Heisenberg group and the corresponding graph.
It has a name because there's the context.
I think this came up in the study in quantum. This group comes on. Yeah. They don't view it like upper triangle. There's a different representation, but it's isomorphic to this. So Cayley graphs can be defined over abelian groups. The first two examples for us was abelian groups. The third one was not an abelian group. So you had to, in order to make it an undirected graph, you had to add in the set of inverses. Sorry, not the. Anyway, you have to add in a set of inverses. Everywhere we ensure that the inverse set of inverses are right. These are, in general, we'll be looking at only undirected Cayley graphs. So S will have both the set of generators and the inverse of the set of generators. So what I want to do in the next 10 minutes, 15 minutes, we'll show that these Cayley graphs are very nice graphs. You see that you already saw it captures the Boolean hypercube, it captures the cycle, the M cycle and all. We would like to understand what is the eigenspectrum of these Cayley graphs. We'll build a single theory which will spit out the entire eigenspectrum of every Cayley graph. Okay. Actually, not every Cayley graph. You can do it for every Cayley graph, but to make our life simple, we'll work only with abelian groups, finite abelian groups. So what we'll do for the rest of the lecture is trying to understand the eigenspectrum of Cayley graphs over finite abelian groups. Okay. And the reason I'm going to define Cayley graphs is later on in this lecture series, this one, in general, when you define graphs, Cayley graphs is an extremely important tool. This is how we'll build a graph. We'll take an underlying group, we'll have a group structure, and we'll build graphs using this group structure. It's a very simple way of doing it. So we'll take a slight detour to try to understand something called characters and stuff, and then come back to understanding the eigenspectrum of this one. So given any, let G be a finite abelian group, things that I say might also work for infinite non-abelian. To make things simple, we'll work only with finite abelian. We will see which of the steps actually fail for the infinite or the non-abelian case as we.
So sometimes for questions about groups, for instance, if you're going to set up Fourier,
Yeah,
it's enough, it's sort of enough to study cyclic groups, and then
it's enough to study cyclic groups.
for eigenspectrum questions also.
It's true, but we won't get the study of that, and this is going to be the same. If there's nothing more simpler, You don't get any further simplification just because you study cyclic groups. What Ronald is stating is if you're looking at just finite abelian groups, every finite abelian group can be written as a product of cyclic groups. So it's sufficient to look at only cyclic groups. Yeah, you can do that. There are places where we'll use that, but not for this one. Here, you can generally put a general or something and it will just work. You want to define the notion of a character. It's literally called a character because it tells you something about the group. A character is some function chi from the group. No, notice the group is an arbitrary set of elements. But we will go to the group which we are most sort of comfortable with, the group of complexes, the complex numbers. And you want it to be a homomorphism. What do I mean by a homomorphism? Is any map of this form satisfying chi g times h is chi g times chi h for all gh in the group. That is basically it's a homomorphism. That is, if you take the character of a product of two elements, where the product is according to the group product, then that's actually the product of the characters of the corresponding elements, where now the product is according to regular multiplication in the complex numbers. These are what's called. That's a definition of a character. Let's make several observations about characters. One, what is chi of the I? But let chi be any character. What is chi of the identity element?
One.
Why?
I mean, chi of, let's say, A dot 1 is.
So you can apply the maybe just write T as T times E. That will tell you that.
That will tell you chi is chi square E. Chi is 0. That's also there. So actually, I should have put up.
The non-trivial character.
Let's put up. I'm working with finite trivial, so let's even start with this one. Chi of G. Right now, the range is complexes. Let n be the size of the group. What do we know then? What is G power n then? No, so G into G into G into G n times. So we do know we'll have to put it to, I'll have to put it to C star. There's no other option. So let's stick to this. What do I want to say? Should I want to say C star? So
This is enough. If you say C star, then
C star, I'm all fine. So there's a stupid character which goes to the all.
If you go to the, if you go to the identity of C star, which will be 1. That's the trivial character.
That's the trivial character. Yeah. So okay. Yeah. Let's do that. So chi e. Now chi e certainly is always 1 for all characters. Okay. Certainly. And there is a character chi which takes G, which maps. There is one character. There is a character, let's call it 1, which maps this character 1 that maps every G to the element 1. This is the trivial character. It doesn't do anything. It just maps. This is what is called the trivial character.
Even if we had the character going to C instead of C star, just that if chi E is 0, then chi of any element ends up being 0. So it's because
No. So I think the way to handle that will be, if I define it that way, there is this one and furthermore, I want the character to be not the function that maps everything to 0.
You're looking at group homomorphism. So you have to decide what group over complex numbers we are looking at.
I'm looking at multiplication.
Multiplication.
So then 0 is out of the picture.
Yeah, 0 is out of the picture. Yeah. So then this is C star. Yeah, fine. Yeah. So it's a group homomorphism, 0 is out of the picture. Yes, fair enough. Okay. So now the next thing I want to ask. Now I'm going to use the finiteness. If G is finite, what do we know about G? So you take any group element, you do the group operation several times. At n times, you will finally end up with identity. Every finite group, this is a process. So for all G, there exists an n such that Gn is E. But then what does it mean? What should chi G be? Chi G will be the nth root of unity. So this in particular says if you are working with finite groups, the range of characters will always be only the complex roots of unity. Even though I put it to be C star, it could be any complex number, the only possible range is complex roots of unity. Hence, chi G to the power n is 1. It is the range of character of pi for every finite group G is the complex roots of unity. So it's all contained on the, in fact, know which complex roots of unity. If the size of the group is n, it can only be the nth complex roots of. It can only be one of these guys. It can't be anybody else. Okay. Fine. Okay. So far, all of this is very abstract. Let's actually see some examples and then continue with some more observations. So let's look at 2 examples. Once again, example is going to be, say, Z, PZ with operation addition. I want to define characters for this. There's, of course, the trivial character which maps everything, each one of these P numbers to the complex number 1. That's the trivial character. But let me define another character. So let me define for each A in Z pi Z, we'll define the character chi A, which takes the element alpha to e power 2 pi I A alpha by P. Is that by P? No, what do I wanted to do? Yeah, that's what I want. Yeah. It's mapping the group element. So just to keep it the group element, let's call this G. That is G. Convince yourself that this was actually a character, because the addition over here becomes multiplication of the exponent, therefore this will be a character.
Inducing the function, inducing the A on chi-isn't
Huh?
like for each we are defining.
I'm defining. So I could have done it for every A. Think of A as some fixed number for now. Think of A as 1 for now. So I'm just defining it to be e power 2 pi I G by P. This is just mapping it to the pth roots of unity. Now I'm doing for A equals 2, I'm not mapping it to the consecutive pth roots of unity, I'm mapping it to the pth root jumping by 2 each time, then jumping by 3 each time. And eventually when A is 0, I'm mapping them all to just the identity element. I'm jumping by P each time. So when A is 0, this is actually the trivial character.
But when A is non-zero, it is going to be negative.
Huh?
They are all going to be mapped. They won't.
For P, for prime P, it
For
will be the same. For non-prime P, this will, yeah. Now when G is F2 to the N with plus, notice, so I gave you an example of why did I give, I told you that there's not just one character, actually produced P characters. As many characters as the number of group elements. You'll see that this is not an accident. Actually, there will be a set of characters, and then for every finite abelian group, the number of characters will exactly be the number of group elements. In fact, there will be a one-to-one isomorphism between the set of characters and the group elements. We'll see that shortly. We'll see that in less than 5 minutes from now. I'm going to define another thing. Similarly, for each F2n, I'm going to define chi-A of B. B is itself B1, B2, Bn. Notice, and A itself is of the form A1, A2, An. This is just going to be product of -1 to the power Ai, Bi. I going from 1 to n. Once again, convince yourself that this is a character. And which is a trivial character? The trivial character is corresponding when A is the all zeros vector. Then all the exponents are 0. Everything is being mapped to the all ones element. These are the parity functions or the Fourier. Yeah, these are the parity functions written on the ±1 basis. Okay. And notice how many, once again, how many characters have I produced over here? I have produced 2 power n characters. You should convince yourself each of them are different characters. They're actually different functions. So the way we're going to go about doing this is we'll actually, so we're going to look at the set of all functions f from G to C. Not necessarily homomorphism, set of all functions. How large, what this is a vector space. So F is a vector space. F is a complex vector space. Is a complex vector space. What's the dimension of the space? Why is it a vector space? I take 2 such functions, add them, I'm going to get another function. I multiply it by a complex number, I'm going to get another function. What is this vector space? This is basically just what is each function? Each function is just a vector of length size mod of G. So write down the truth table, that's all it is. So this is just a with dimension mod G, that's all. Each vector, each function here is just a vector of length mod G. That's all it is. And you're doing, that's all happening over here. So
the fact, for example, in Fourier, we know that those are orthogonal and things like that.
We haven't yet come to any of that. We will soon come to that.
Those are more general.
They're more general. We'll come to all of them. We're gonna. So you want to show some orthogonalities or something. So we'll define an inner product on the space. So let's equip the space. Equip the space with an inner product. What's the inner product? I'm going to. So I'm going to from F cross F to the complexes. What's the inner product I'm going to go? The FG, inner product of them is going to be summation G in G. H. This is an inner product. This is the usual inner product when you're working with complex vector spaces. What we shall do, we'll actually now get back to this one. We'll ask how do the characters behave under this inner product. Okay. So we continue our observations. We had what observations? Observations continued. I want to say if chi is a character,
Right, that's no. So if it's a vector space, the all zero vector should be there, right?
yeah, it is there. I didn't say the characters are a vector space. So far, I just defined this to be a vector space. And I equipped a form in a product on that vector space. Characters are some elements of this vector space.
Get some, yeah, such.
The characters are some elements of this vector space.
I thought we excluded the zero.
No. This vector space has.
They still have it.
This
Huh?
is the span of all G-dimensional vectors.
Yeah.
Yeah.
That's fine.
Yeah. If chi is a character, I want to say chi inverse, which is just element wise, is also a character. That should be clear because if chi inverse will also be a character, it's also going to be a homomorphism. If chi is a character, chi inverse is also a homomorphism.
Right.
Chi inverse is element point wise, you take the inverses. Chi inverse of G is 1 over chi G. Okay, now I'm going to do this one. We're going to look at summation of chi G, G over G. We look at this guy. This is size of G if chi is trivial. And we'll prove it to be something else otherwise. This would be a very useful fact. Is trivial, then it should be clear. Chi of G, G is actually size of G. Suppose chi is not trivial. Then there exists some G prime in G such that chi of G prime is not equal to 1. In particular, some element is not mapped to 1 because it's not the trivial character. So let's look at this sum chi G, G in G. I want to claim this is the same as chi of G, G prime, G in G, where G prime is this one fixed element that I have worked. Because multiplication by G prime is just going to permute the elements of the group. But what is this? Because the product of this one. What is chi of G, G prime? So I can take out chi G prime outside. So this is chi G prime times chi of G, G. But then what do you get? It has to be 0 because we know chi G prime is not 1. Therefore, there's some quantity which is the same as that quantity itself multiplied by non-1. Therefore, the only way that can happen is that quantity. So, for every if chi is any other character, the sum has to be not 0. So there is this quantity that we have here. It's the same quantity we have multiplied by something. So we have A equals alpha times A, and alpha is not 1. The only way that can happen if A is 0.
So we are having the character to have zero.
No, we are not allowing that. It's just the sum of the characters is the sum of the range. I'm not allowing a character to be 0. I'm just stating that if I take a particular character, it gives complex roots of unity for the various group elements. If I sum that up, it says it will sum to 0.
Take the expression on the left, the expression on the right, bring it to the right.
Yeah, so like I'm talking about like chi g prime here.
Yeah, so
Yeah.
chi prime, if as long as chi g prime is not 1,
Chi g prime is not 1.
The way we define it to C star.
Yes.
Yeah. So it can be 1. Right?
But the one plus person they can cancel each other.
I don't follow it. No. So let's do this once again. So what haven't we got this? We have got the following. No. The sum above equation can be written as sum. It's just chi g prime minus 1 into summation chi g. This is equal to 0. We have proved this. Now, if this is the case, if the product of two things is 0, one of them has to be 0. We have chosen g prime so that chi g prime is not 1. Therefore, the second one is 0. Hence, summation chi g. Okay. What Mrinal said will be useful, but anyway, that's no. So, want to look at now the inner product between two characters, chi and chi prime. What is this? So chi and chi prime are two functions in the vector space. I'm just taking their inner product. By definition, this is summation g in g, the conjugate of chi g times chi prime g. Okay. Observation, postulation, added more. If what is the conjugate of, I want to say the conjugate of a character is also a character. It's also homomorphism. It's exact same. Yeah. In fact, it is the inverse because for the case of finite groups, the conjugate will in fact be, will the conjugate be the inverse? No, conjugate won't be the inverse. So it's also a character. Okay. It's, yeah, this one. It's this one. And you have another property.
Product of two characters.
The product of two characters is also a character. If chi is a character, chi 1 is a character, chi 2 is a character, that's also a character. Therefore, this is exactly summation g in g. This particular characters huh? If unless it's a trivial character. Trivial character. But what is, so this is 0 if chi prime chi is not equal to 1 and 0 if sorry. But let's look at this condition carefully. When will this happen? When they are inverses of each other. When chi conjugate is the inverse of chi prime. In particular, that will happen only if chi is chi con. This will happen only if chi is equal to chi prime. Observe. Chi prime chi is 1 if and only if chi equals chi prime. Therefore, you get the following. You get that this is 0 if chi not equal to chi prime and size of G otherwise. Yeah. What did I do? I messed it up. It's not equal to and yeah. So the inner product of two characters is 8. If there is the same, it's mod G. Otherwise, it is 0. So the characters are always orthogonal. The characters are always orthogonal in this space. Huh? Okay, now I would need what? Now said, I think I will need that property. So every finite abelian group, for every finite abelian group, we constructed, for every cyclic group, we constructed, so the cyclic group is say M. This is true even for non-primes, by the way. I can put an M here and M here. There's nothing about prime that I'm using here. For every cyclic group, I have constructed for every cyclic group of size M, I have constructed a set M characters. Now, for every finite abelian group can be written as a product of cyclic groups. I will use this property here, but I will not. But I'm going to use the property. So any finite abelian group group G can be written as the product of cyclic groups. So G can be written as, say, CM1 cross CM2 cross CMR. The size of G is the product of the MIs. But,
why chi prime equals to 1 if only chi equals to chi prime?
Just check it out element by element. That is the only way it will happen.
It will not be chi bar is not the inverse of.
One second.
They are all on the unit circle. So chi bar, so everything, these are complex numbers on the unit circle. So chi bar is just the angle will just be, you reflect it on the x-axis.
Yeah.
Which will mean that chi prime of alpha should equal. I think it's true.
This is true. This is true.
Just has to be written. Like if you write it down.
Because there are things on the unit circle, this happens. I should say it properly. Yes. Yeah, because they are in the unit circle, this happens.
E to the I theta percent theta. And then you take a bar of it.
It becomes e to the minus I theta.
That's the only way it can.
And therefore, yeah. Yeah. So I want to get characters for this group. For each of these groups, I know how to get characters. For in particular, I told you, so suppose we take an A1, A2. So take A1, A2, AR in Z M1Z cross Z M2Z cross Z MRZ. We had constructed a character chi A1 for the group CM1. We had constructed character chi A2 for the character CM2. And similarly chi MR for the group CMR. We had constructed all such characters. I'm just now going to construct a character chi. Let's call it A bar of an element B bar to be just B1 times B2 times B. So notice that this is also a character. The design. I'm just taking the characters for each of the individual cyclic groups and taking the product of the corresponding characters. This will be a character for this one.
But in this statement, they don't have to be distinct. MIs don't have to be distinct.
MIs don't have to be distinct or anything. Yeah. You can, in fact, you can get a much nicer structure, but I don't need any of that for this proof. This proof will just come. Yeah. So what have I got at the end of this? Notice because of this structure. No, so let's pause. What did we get out of 6? 6, we showed that all the characters are orthogonal. Now, let's look at the specific case when the group is the cyclic group or the F2N group. We actually produced the number of characters we produced was equal to the size of the group. Therefore, these characters are not just orthogonal; they form an orthogonal basis for the group because they actually they are exactly the size matches the dimension of the group. So in these two cases, we did have that the characters are not only an orthogonal set, but actually an orthogonal basis for the group. I want to claim this is true in more general, and that's because of the finite abelian structure. That is, any finite abelian group can be written as a product of cyclic groups. Therefore, I can come up with characters. A character for the group G can be just got by product of characters. Therefore, I have how many characters I have produced here? I have produced. So the above produces. This procedure produces mod G characters. They all have to be orthogonal. They all have to be orthogonal. Therefore, they are on orthogonal basis. Firstly, the orthogonal basis, there can't be any more characters also. Because he has shown that the characters are orthogonal and these have already formed an orthogonal basis for the space. There can't be any more characters. So we understand for finite abelian groups, the set of characters form an orthogonal basis for the set of functions going from the group to the complex. Conclusion, the corollary of all of this is for every finite group, finite abelian group, G, the set of characters form an orthogonal basis for F, the set of functions from the group to the complex under the inner product we defined. Under this inner. Okay, it's a whole detour of characters that we take, but let's come back to. Okay, so characters for, if you have a finite abelian group, the set of characters form, in fact, I explicitly told you what are the set of characters. If you know how the finite abelian group can be written as product of cyclic groups, you know the set of all characters. And in fact, you should realize this F2N, that's exactly how I got. Where is F2N? This is also corollary of this. The F2N is the product of n cyclic groups of size 2. And that's exactly the product of the corresponding n characters. That's what's happening there. The character there will be just the character which takes either everything to 1 or to 1 and -1 for each of the cyclic group of size 2. And this is the product of them. That's exactly what's happening. So actually, I don't need example 2 also. I only need example 1 and the finite structure. Everything follows from that. Okay. All of this was a detour of this one. Let's return to Cayley graphs. So G is a finite abelian group. S is some set of generators. Such that S is equal to S inverse. And let the graph G be the Cayley graph corresponding to G comma S. Now let's look at A G be the adjacency matrix of this Cayley graph of G. And chi some character of the group G. Notice the character does not depend on what the set of generators is. The adjacency matrix, of course, depends on what the set of generators is. The adjacency matrix is a mod G by mod G dimensional matrix, which will have ones at the right places based on when G is connected to GS. That's exactly what it's going to be. The character is just a function of the group. It has nothing to do with the set of generators. But let's look at what does the adjacency matrix do when you multiply it by chi. So let's look at the Gth element of this. What is this going to be? This is summation overall. So no, AG is a G cross G matrix. Chi is a function on G. So there's a very natural. Yeah. So let's see. Huh? Element wise, yeah.
The matrix vector.
It's a matrix vector. This is a matrix. That's a vector, and I'm making a matrix vector, and I'm asking the Gth element of that matrix vector product. So this is a vector now, and I'm asking what's the. So this is a matrix. This is a vector. This is a matrix vector product, and I'm asking what's the Gth element of that. Okay. Notice this is exactly, you're going to pick up all the neighbors of G in this graph and the sum of chi on that. So this is exact. And what are its neighbors? It's just chi GS. Those are the neighbors of this. But because it's a character, what is this? This is chi G into chi S. S belongs to S. Which is what? Which is summation S chi S. Chi G comes out. So what does that mean? AG, this matrix times this vector is always times chi. And done it element by element for the vector. Therefore, this is true. This vector is the same as this vector scaled by this quantity. This quantity is independent of G. What does that mean? Chi is an eigenvector for the matrix AG. This is the matrix A. In other words, chi is an eigenvector for AG with eigenvalue summation chi S and S. So in fact, because we have n eigenvectors, we have n characters, we have got all the n eigenvectors already. They had to be mod G. We already showed mod G characters in the previous discussion. Now we have shown this is a graph on mod G vertices. We have given mod G eigenvectors. And so these are all the eigenvectors of this particular adjacency matrix. So for Cayley graphs, we fully understand their eigenvectors. Their eigenvectors are exactly the characters of the group. And notice these eigenvectors, it didn't matter. You can take any set S of generators. The set of eigenvectors is the same set of eigenvectors. The eigenvalues will change depending on which set of generators you use. The eigenvalues will be this one. But once you fix a particular group, whichever Cayley graph you take on it, that is in whichever set of generators, the eigenvectors are the same set of eigenvectors.
So just scroll a little bit, what are the things we define? So S for some set of generators.
So you start with the group G. Group G defines the vertices of this graph. S is a set of generators which is telling you which vertices are connected to which. This one. So now there's a choice of which S you could choose.
So the matrix A script G, the rows and columns are indexed by the elements of the group, and any entry of the matrix is going to be a generator.
No, any element. So when will an entry be 1? If that group, that row and that column, if they can be obtained from each other by multiplication by a generator element, then you put a 1 there.
Okay, so it's not okay. The element entry is not saying which generator to Q from G to G prime.
No. So you're asking, is the entry AG, is the entry corresponding to G and G1 and G2 1 or 0? It is 1. It is 0 if G1 can be got from G2 by multiplying by a generator element.
And then the chi is just some
chi is just some function on the group, some complex function on the group, which is a homomorphism. Now this one clearly says because it's a homomorphism, a character has to be an eigenvector.
Yeah.
Every homomorphism is an eigenvector of the Cayley graph.
The characters are the eigenvector is invariant of S. Is that also we are saying?
Yeah, I was, because notice that the definition of characters did not depend on what S is. Therefore, I take any Cayley graph on this particular group. That is, I choose one set of generators S1, I choose another set of generators S2. The eigenvectors for both these graphs are the same set of guys. The eigenvalues differ. The eigenvalues are these guys. Okay, and that's quite an amazing. By the way, because of this, you can now go write down what is the eigenspectrum of the Boolean hypercube of the cycle. We have the characters. You know the generators. So for each of the eigenvectors, you know what are all the eigenvectors. You can go for each of the eigenvectors, go and write down what are its eigenvalues. We have for the cycles, and at least cycles and Boolean hypercube, we have the complete eigenspectrum with us at this point of time. Okay, and this is a very useful thing. No, we will. And this is for the adjacency matrix. Notice these are regular graphs, therefore the Laplacian will also have the same eigenvectors. The eigenvectors will remain the same for the Laplacian, except so for the Laplacian we'll have the same thing. So that's just because the Laplacian. What is the Laplacian of G? Is just the degree of G minus the adjacency matrix. And this is just size of S into I minus the adjacency matrix, because these are regular graphs with the degree being size of S. Therefore, that's this one. Therefore, the characters are going to be the eigenvalues of both the Laplacian and the adjacency matrix with eigenvalue this or mod S minus this. That's all it's going to be. So that's right. Okay. Chi, character of G, is an eigenvector of adjacency matrix with eigenvalue summation chi S, S in S of the Laplacian G with eigenvalue size of S minus IS. More times. Okay, cool. So Cayley graphs will appear all over the place. We'll see Cayley graphs all over the place. And the nice thing about them is Cayley graphs, we fully understand the eigenspectrum because of this theorem. Cayley graphs, when you have a Cayley graph, the eigenspectrum is exactly the eigenvectors are the characters, and you know also the eigenvalues. Okay, you can change topics. We'll move to what are called random walk matrices. So we'll define it very generally, but let's start with the simpler case. Let's start with G being an undirected, unweighted graph, but not necessarily regular. This is a natural random walk that we can define on this graph. Suppose you're at some point in the graph, you pick a neighbor at random and go to the neighbor. There's a natural random walk we want to define, and we want to understand properties of this particular random walk.
Sir,
Yeah.
to use this Cayley eigenspectrum of Cayley graph. So in general, I mean, we are just given the graph. We have to identify G and S.
So you have to find out if firstly the graph, if the graph were Cayley, that is, if you can identify the vertices with a group and the edges with this group structure, then we get this one. It is not always the case. The Boolean hypercube and cycle movement, for example, if the graph is not regular, this is not true. The graphs have to be regular and furthermore have the super nice structure.
Is there some maybe anything to do to check if it is some Cayley graph, Cayley graph? Besides regularity is a trivial check.
No, I do not see. For example, there's this graph, which we will see later on, which we'll study later on, the infinite D tree. It's an infinite graph. Take a vertex, connect it to D neighbors. Then take another vertex, take each one of itself, connect it to D minus 1 neighbors. So it's basically this graph, which right here. So infinite D tree. Yes. What's an infinite D tree? You have a vertex connected to D neighbors. This is D. Then connect these to D minus 1. Each of these to D minus 1. Each of these to D minus 1. Now, once again, these to D minus 1. So the degree of every vertex is D. The root alone is D because it doesn't have a parent. Everybody else has D minus 1 because it has a parent. So this is what it's an infinite. This is called the infinite D array tree. We will study this quite often when we do expander graphs. It's supposed to be the best expander. Notice that I don't see an easy way of looking at this as a group structure. We will identify the vertices with some group, we'll put it on top of it, we'll look at it as group operations and all. It's not easy to do this. We will see all of this later on. Not infinite tree. We'll see this later on while studying expanders. So I don't know an easy way of checking if a graph is given a graph to find out what is the group you want and because you have to identify the vertices with some group. I don't know how to do that. But let's go back to this random walk. So I'm given G. So there's a very simple random walk, which is at each step, choose a random neighbor. It's a random neighbor. So what is the probability that you go from the vertex U to the vertex V?
B is the neighborhood of then
Yeah, so it's exactly AG of U comma B. Firstly, that tells you whether it is 1 or not, divided by the degree of U. So and in general, this is the matrix. So the random walk matrix is going to be this matrix. We are going to study this matrix W U comma V, where the UVth entry is probability of U going to be. So I'll build a random walk matrix. We'll study more general random walk, but this is a random walk matrix that comes from an undirected, unweighted graph. Now, you could drop the weights. For example, we could generalize this to, generalize to.
Is it the probability of there is an edge between U and B? Or is it there is a path between U and B?
There's an edge. So you only go to the neighbor. So you move to a random neighbor. So this is only, that one arrow is just an edge for now. Yeah. So generalize to weighted graphs with with positive weights, non-negative weights. So suppose so far I worked with the undirected for just unweighted graphs. Now, if you want to do the random walk on weighted graphs, what will you
the probability of the weight.
So you look at the sum of the weight of the edges going out of you. Pick an edge proportional to these weights. So in particular, what you're going to do is this probability of UV is going to be the weight of UV divided by the sum of weight of U comma V prime over all V and V. That is, you're looking at all neighbors. So we will define degree in a slightly more. So if we define, so let's suppose adjacency matrix, you just put the weight. Adjacency matrix UV, you just put the weight between U and V. And I define degree to be this more general notion. It's just summation of weight UV of V and V. Then this is exactly the same as before. This is just AG UV by degree of U. So this all I'm saying is even for weighted graphs, we can take the same notion, whereas I'm going to define degree now not to be the number of edges, but the sum of the weights of the edges leaving this particular graph. But we're working with undirected this one. So these are one. What we would want to understand is we would eventually want to understand what the goal is. We are trying to understand the eigenspectrum of this matrix W. That's our goal.
V prime belongs to N of U.
Because neighbors, we are assuming that the non-neighbors will have all 0. The weight will be 0, therefore it doesn't, when I summation, it doesn't matter. in particular the random walk matrix, the W looks like the W matrix is exactly this matrix. If you recall, the WG is DG inverse AG. AG is where AG is the adjacency matrix. Possibly weighted adjacency matrix. And DG is the diag of the degree. Just put the degrees, now possibly sum of weights. Degree is not sum of edges, but degree. This one. What I would like to understand is, we would like to understand properties of random walk. We'll try to understand it via understanding the eigenspectrum of this matrix WG. Notice WG is not a symmetric matrix. If the graph was regular, then it's a symmetric matrix, because then this is a symmetric matrix and you're multiplying one, then it will be a symmetric matrix, then you'll have it. If DG graph is not regular, this is not a symmetric matrix. Therefore, we don't even know if it has an eigenspectrum, because it's not self-adjoint under the classical dot product. So we'll have to work for that a little more. But how are we doing with respect to time? Just say a few more things and then stop. But more generally, we'll be interested in. So right now, what I have defined, we have a weighted adjacency matrix, a weighted graph given to you, a weighted undirected graph given to you, and from that you can build a random walk matrix, which is exactly this is the random walk matrix I'm constructing. But more generally, a random walk matrix W is any matrix in R n cross n or V cross V. In fact, R greater than or equal to. All the entries are where WUV just represents the probability you go from U to V. So you must have such that for all U, we must have summation WUV. V in V should be equal to 1. As long as it is what you call a row stochastic, then this is the matrix corresponding to some random walk. Not all random walk matrices come from weighted undirected graphs. More generally, we would want to study these sort of walk matrices. And note
the only generality is that it could be directed.
Yeah. Not all random walk matrices, yes. Random walks arise from, if you assume directed, then these are the same. There's nothing. So arise from weighted undirected graphs. So in general, in the study of random walks, you would want to understand any random walk, which is a weighted directed graphs. But what we are trying to understand is via the eigenspectrum. We'll say that we won't be able to understand all random walks. We'll only be able to understand a certain class of walks. And in fact, all those walks will be actually weighted undirected graphs. Random walks arising, and we'll see that too. We'll see that only for those graphs will we have an eigenspectrum, and we'll be able to prove certain things. But I have 2 minutes. Let me just. So notice W is not a symmetric matrix. W is not a symmetric matrix. So right multiplication by a vector and left multiplication by a vector are two different operations. They do two different things. Let's try to understand for a random walk matrix what is right multiplication and what is left multiplication. I also forget what is right and what is left. I have one confusion what is right and which is to the right and which is to the left. I do not know. Is a matrix to the right or so I will call something right, something left, and just believe that is right. Right. Yeah. As long as I call it two different terms, it's well and good. So let's talk about what's right multiplication first. So I have F, which is in RV, and W is a random walk matrix. Will be done before the power-itize it. What is WF? So WF is some vector, no? You're multiplying. This is a right multiplication I'm doing. I'm multiplying which one on the right? I'm multiplying the vectors on the right of the one. What? So what is WF of, say, the vth entry? What is this? By definition, what is it?
One step of.
So no, but let's write it down. This is U over V, WUV, FV. So what does this represent?
Okay. They're looking at the V entry, so you should do something.
Sorry. Then I want this to be U. WUV, FV. So what is this? So think of F as some function on the set of vertices. Now you take one step in the graph. This is the expect. So there's a function on the vertices. You take one step on the graph. This is the expected function you see on the graph. This is how the function, the expected function changes. That is, you're at a particular location, so you have some function on the graph. Then you take one step. Now you're asking how does the expected function. Now you're no longer at a fixed step. You are at a different set of vertices, and you're asking what's the expected value you see. This is it. Therefore, what WF does is how F evolves as you walk on the random step. So think of F as some function on the vertices, and how this function, the expected value of this function as you take the random walk is what WF. So WF will ask, if you take one step, how does the expected value of the function? W square F will play, if you take two steps, what will be the expected value of the function at each location? So WF, the right multiplication, basically is trying to understand. Right multiplication is understanding how does a function evolve, function on the vertices evolve with the random walk. In particular, what is a function? What is an eigenvector in this case? Is there one eigenvector? Is there one function that doesn't change at all? The all ones function, the constant function, will not change. So in particular, because of row stochastic. Yes, this is this one. So the all ones is always a right eigenvector. Let's just do left multiplication and stop. Let's find out what left multiplication does. So here now P is some R and V. Once again, W is the random walk matrix. For me, all vectors are always column vectors. So I'm going to write this as P transpose W. Because any vector for me is a column vector. Therefore, if I have to put it on the left, I had to make it into a row vector. So it's P transpose W. So let's ask. Let's ask what the vth entry of this is. What is this? This is exactly summation P of U PU WUB. So what is this? If we think of P P could be any vector, but let's think of P as a probability distribution on the vertices. Then this is the new probability distribution you get on the vertices by taking one step. So suppose you were in a particular probability distribution on the vertices. This is what's the new probability distribution after taking a step on this one. This is how the probability distribution evolves. So if P is the probability distribution on vertices, P transpose W whole transpose, because that's a row vector, I have to make it back into a column vector, is the probability distribution after one step of the random walk. So left and right multiplication correspond to two different things, right? Left multiplication is you have a function on the vertices and how that function evolves with a random walk. Right multiplication is there's a probability distribution on the vertices, and what is the probability distribution after one step? Therefore, for the random walk, which will happen is you go from P transpose, this will be the random walk. You go to P transpose W, one step, the next step will be P transpose W square, P transpose W cube, and so on. Is how the random walk, this is how the distribution evolves with time. If you're working with symmetric matrices, these are the same thing, but we will be working with two different objects. One side will be functions, one side will be this one. That's why I'm doing this more pedantically in a much slower fashion. So these are the left side. That's right multiplication. This is left multiplication. And a probability distribution that, so you can ask what are the eigenvectors over here also. What is an eigenvector? We will see. I'll not do it this time. There will be one probability distribution which remains unchanged. And that will be the stationary distribution. So that will be an I. So any probability distribution pi such that pi transpose W is equal to pi transpose is called the stationary distribution. It's called a stationary distribution at this point. We haven't shown. We'll soon see that under some conditions, actually the stationary distribution will be unique. And we'll use the stationary distribution to define, to do further work on this graph. Okay. So the stationary distribution is an eigenvector with eigenvalue 1 is a left eigenvector. Is a left eigenvector with eigenvalue 1. The all ones vector is a right eigenvector with eigenvalue 1. There are two different things. If the matrix had been symmetric, these would have been the same object. We will look at this. Based on this, we will come up with, we'll ask, firstly, the first question we'll ask is, when do you have a stationary distribution? We'll show that at least for graphs arising out of weighted undirected graphs, there will always be a stationary distribution. In fact, the stationary distribution will be the distribution which is proportional to the degree. That will be the stationary distribution. We'll show that that's a stationary distribution. We'll ask, when is it the unique stationary distribution? So those two we have got. But this is not enough. We want to understand this one. We want to understand the eigenspectrum. It's not a symmetric matrix. So what we'll then do is we'll define a new inner product, not the classical dot product. We'll define a new inner product and show that some matrices, random walk matrices, are self-adjoint under that inner product. Therefore, you will have a full eigenspectrum, and we'll use that eigenspectrum then to study the properties of the random walk matrices. So that's what we'll do in the next lecture. And the lecture after that, we'll begin the Cheeger inequalities. Okay. Let's stop. Then from next lecture, we'll go to the original schedule of the course, which is Monday and Thursday.